Now let's understand the loss function. For now, ignore the first term. The first summation sign is for each grid value, which is 7 cross 7, with a total of 49 grids. The second summation is for 2 boxes for each grid. These are the actual and predicted coordinates values for each object in each grid. Now we know that many grids do not have any objects, so for those, we cannot have ground truth labels. To solve this problem, we added this extra switch, which is 1 when that grid has an object and its coordinates, and it turns 0 when there is no object in that specific grid. Thus, the entire loss for that specific bounding box of that specific grid turns 0. The next part is the same as the previous part, but this time for width and height. The only difference is this underroot part. To understand this, let's consider 2 bounding boxes, one with width 20 and height 30, and another with width 4 and height 6. The predicted bounding boxes for the first are with a width of 18 and height of 27, and for the second predicted bounding box is of width 2 and height 3. Now, if we calculate the loss for both bounding boxes, the total loss will be the same, but we can clearly see that the first box is almost accurate, and the second box is half the size of the ground truth box. So we want our neural network to focus more on this small box and predict it more accurately. By taking the underroot of the width and height, we can give more focus to small bounding boxes, so we can get more accurate bounding boxes for small objects also where it previously was focused on large bounding boxes. In the third and fourth lines of the loss, again we are taking the mean squared error for the confidence score for whether an object is present or not. Here, as we discussed earlier, this represents values of 1 if an object is present and 0 if no object is present. The second part is the opposite of the first one. The actual goal is to use this as a loss if there is an object, and if no object is present, then use this second part. We multiply this second part with a small value of 0.5 to give less importance to the loss of error if there is no object. This is because most of the grids are usually without objects, so this part of the equation already gets a lot of attention, and the model gets biased about no object. Now, to the last part of the loss equation. Here, the first part represents different grids, but the second part has the same class for both bounding boxes for each grid. This is for class prediction loss. The only thing left is this sign, which is the value of 5. This increases the loss for these first 2 equations to force the model to focus more on predicting correct bounding boxes. This was the first YOLO paper except for one thing. The X and Y values in the output neurons in YOLO 3 are the top left corner coordinates, but in YOLO 1, they are the center of the box, relative to the bounds of the grid cell which predicts the bounding box. Share your feedback in the comments section.